Before we discuss the phase equilibria of systems with two or more components, let's introduce the concept of solution. A solution is a special type of homogeneous mixture composed of two or more substances. In principle, the component with the largest fraction is the solvent. The other components are the solutes. We say the solutes are dissolved in the solvent. For example, when sodium chloride is dissolved in water, water is the solvent, while sodium chloride is the solute. However, if a solid and a liquid form a solution, the liquid is called the solvent, even if the solid has a higher fraction. For example, when 150 grams of calcium nitrate is dissolved in 100 grams of water, calcium nitrate is the solute, while water is the solvent. Though in most cases, the solutions under discussion are liquids, the mixtures of gases are also solutions. The homogeneous mixture of two solids with a single crystal structure is a solid solution. For example, in the system composed of A and B, alpha is a solid solution, in which A is the solvent, while B is solute. On the other hand, beta is another solid solution, in which B is the solvent, while A is the solute. Alpha plus beta is a two-phased area where the two solid solutions, alpha and beta, coexist. There are a few ways to measure the concentration of solute in a solution. In industry, mass concentration is widely used. The mass concentration of a component is the ratio of the mass of it to the total volume of the solution. The mass fraction is also widely used in industry and daily life. It is the ratio of the mass of a component to the total mass of the solution. The mole fraction is widely used in science study. It is the ratio of the amount of substance of a component to the total amount of substance of the solution. The volume fraction is the ratio of the volume of a component to the total volume of the component prior to mixing. Pay attention, the volume of the solution may be different from the total volume of the component prior to mixing. In the mixture of ideal gases, the mole fraction is identical to the volume fraction. That is because, at certain pressure and temperature, the volume of ideal gas is proportional to its amount of substance. Please pause the video here to check an example of the conversion between different measures of concentration. The molar concentration, also known as molarity, is the ratio of the amount of substance of a component to the volume of the solution. It is widely used to describe the concentration of liquid solution in chemistry. The standard molarity, 1 mole per liter, is usually used as the standard state of a solute. Related to molar concentration is the number concentration. It is widely used in physics. Number concentration is the ratio of the number of particles of a component to the volume of the solution. It is proportional to the molar concentration. The proportionality coefficient is the Avogadro constant. The molality is the ratio of the amount of substance of a component to the mass of the solvent. The standard molality, 1 mole per kilogram, is also used as the standard state of a solute. When the concentration is very low, the mass of the solvent is close to the mass of the solution. Then, the molality is proportional to the molarity. The proportionality coefficient is the density of the solution. When the solvent is water, the density is 1 kilogram per liter. Thus, the numerical values of molarity and molality are identical. Meanwhile, the standard states defined with standard molarity and standard molality are also identical. Solubility is ability of the solute to form a solution with the solvent. A saturated solution is a solution in which no more solute can be dissolved. For example, this picture shows a saturated solution with crystal of the solute. Solubility also applies to solid solutions. We can use a CT diagram to understand the solubility. At a certain temperature, the maximum concentration of B in A is the phase boundary between alpha and alpha plus beta. Below this concentration of B, there is only one phase, alpha. Above this concentration, no more B can be dissolved in A. Another phase, beta, appears. On the other hand, the maximum concentration of A in B is the phase boundary between beta and alpha plus beta. Below this concentration of A, there is only one phase, beta. Above this concentration, no more A can be dissolved in B. Another phase, alpha, appears. Obviously, the solubility depends on temperature. Solubility is measured as the concentration of the solute in the saturated solution. Since there are various ways to measure concentration, there are also various ways to measure solubility. The most widely used measure of solubility of aqueous solution is the mass of solute per 100 grams of water. Since the density of water is 1 gram per milliliter, the solubility can also be measured as the mass of solute per 100 milliliters of water. The values are the same. Please check the following example of the calculation of the concentration of saturated sodium chloride aqueous solution. If two substances have no solubility limit, that is, they can form solution in all proportions, they are said to be miscible in all proportions, or just miscible. For example, water and ethanol are miscible. The mass fraction of ethanol can be from 0 all the way to 1. For a pair of solute and solvent, if the solubility is extremely low, the solute is said insoluble in the solution. The thresholds to describe something as insoluble may depend on the application. It is usually 0.01 to 0.1 gram per 100 grams solvent. For example, barium sulfate is insoluble in water. Its solubility is 0.000245 gram per 100 grams of water. That is why you can see precipitate when mixing barium cations and sulfate anions. Now, let's consider the thermodynamics of mixing. We start with ideal gases. Suppose two ideal gases at identical temperature and pressure are isolated by a partition. When the partition is removed, the two gases mix spontaneously, since the increase of entropy. The Gibbs free energy of mixing is the sum of the Gibbs free energy of their isothermal expansions, because ideal gases have no interaction with each other. The Gibbs free energy of an isothermal expansion of ideal gas is expressed with the initial and final pressures. The initial and final pressures can be replaced by the initial and final volumes of the free expansion, which is its volume fraction in the final mixture and is identical to its mole fraction. Thus, the Gibbs free energy of the free expansion of one gas depends on its mole fraction. So is the other gas. Pay attention, there are only two components in the system. The sum of the two mole fractions is 1. So, the Gibbs free energy of mixing is determined by the mole fraction of one gas. Here, I show you the plot of Gibbs free energy of mixing as a function of the mole fraction of gas 1. It is always negative for any fraction and has a positive second-order derivative. That means, the single-phased mixture has lower Gibbs free energy than any combination of two phases. So, gases are always miscible. The entropy of mixing can be also derived from the Gibbs free energy of mixing. It is always positive, as we can expect. Note that, the entropy of mixing is independent of temperature. In ideal gases, the enthalpy of mixing is 0, because there is no interaction between two gases. In contrast, in condensed phases, the enthalpy of mixing depends on the interaction between particles significantly. Here, we discuss the solubilities of the solutes which do not dissociate into ions. The solvent also remains as molecules. If both the solute and the solvent are nonpolar substances, the main interaction between their particles is London dispersion force in both. The main interaction between the particles in the mixture is still London dispersion force. Thus, the enthalpy of mixing is very small, and the Gibbs free energy of mixing is still negative due to the entropy increase. If both the solute and the solvent are polar substances, the main interaction between the particles is Keesom interaction in both of them. The main interaction between the particles in the mixture is still Keesom interaction. Thus, the enthalpy of mixing is also very small, and the Gibbs free energy of mixing is still negative due to the entropy increase. The situation is totally different in the mixture of polar and nonpolar molecules. The interaction that contributes most to the enthalpy is the Keesom interaction between the polar molecules, because Keesom interaction is much stronger than the London dispersion force between nonpolar molecules and Debye interaction between polar and nonpolar molecules. Furthermore, the mean distance between the polar molecules increases due to the mixing, which increases the enthalpy of the system significantly. Thus, the enthalpy of mixing is considerably positive, making the Gibbs free energy of mixing positive in normal conditions. In conclusion, substances with similar polarities are likely to have high solubility in each other. It is similar to the phenomenon that substances with similar polarities have high wettability. For example, benzene and toluene are both nonpolar substances. They are miscible. Water and ethanol are both polar substances. They are miscible as well. In contrast, water and benzene are insoluble in each other. Nevertheless, ethanol, as a polar substance, is miscible with benzene and toluene. That is because ethanol is not as polar as water. The solubility depends on temperature because the Gibbs free energy of mixing depends on temperature. The calculation of enthalpy of mixing is complicated. A rough model shows that it is proportional to the product of the mole fractions of the two components. Based on this model, we can find that, at high temperature, the Gibbs free energy of mixing is always negative, and has a positive secondary derivative because the entropy of mixing overwhelms. On the other hand, at low temperature, the Gibbs free energy of mixing shows two minima. That means, at a fraction near 0.5, the Gibbs free energy of mixing is higher than two separate solutions with fraction x prime and x double prime. Therefore, the mixture separates to two phases spontaneously, and the substances are immiscible. The highest temperature at which phase separation occurs is the critical temperature. Here, I show you a CT phase diagram of methyl acetate, carbon disulfide system. Both are categorized as non-polar substances, but methyl acetate has a small dipole moment. Above the critical temperature, only one liquid phase exists. Below the critical temperature, only one phases exist when x is below x prime or greater than x double prime. Between x prime and x double prime, two phases coexist. The two-phased range shrinks with temperature. Pay attention, the enthalpy and entropy of mixing are sometimes heavily temperature dependent. In that case, the phase diagram can be much more complicated.